Hi everyone. My name is Thomas Planco, and I work at Argonne National Lab. So I will start a few slides explaining what we do at Argonne and after our project. And I call it a little fancy, like a tracepoint factory, because we are a small team with a lot of tracepoint, and I will show you maybe how. So we are really the end user, as we say. So we are already like using tracing, and I maybe want to give you a little summary of what we are doing. Depending on your background, either we do a lot of tracepoint or a small tracepoint. I guess it depends. If you work at Azure, it will be a smaller tracepoint. If we work at small university, it will be a lot of tracepoint. So we work at Argonne National Lab. Argonne National Lab, our specialty is HPC, so high performance computing. And for the past now 8 years, I work on Aurora. So Aurora is a supercomputer. And it is what we call an exascale machine. So it can do an exascale double precision calculation per second. For more real number, it does so 10,000 nodes. So I think it's maybe, I don't remember how many racks, but it's a pretty big room. I guess it is maybe 4, 5 basketball field. And we have 6 Intel GPUs. So maybe surprise, Intel is doing GPU, or was doing GPU, I don't know. But at least it is 6,000 GPUs, and this is what we want to trace. So this is our scale and an objective, and to be able to, some people in our lab, some of our users is running at full scale machine, so they are running the same job, the same HPC application on this number of GPUs, so 60,000 GPUs. So 12, so, and because we have 2 more, so I mean, you multiply by 10 for really the number of MPI processes, so number of processes we are running. So at the beginning of the project, Intel arrived to our system and say, okay, as all the big company does, they reinvent everything. So they say, okay, we'll use what they call level 0, which is their CUDA. It is a CUDA of Intel. And they didn't provide any tracing capabilities. So we wanted to be able to trace, to understand what the program we are doing and how to optimize. So me and Bryce, we work at the performance engineering group, and our goal is to find performance bug into runtime, into OpenMP runtime, SQL runtime, or level 0, whatever, into application. So we wanted to trace, so we developed a tool we called TAPI, would mean tracing heterogeneous API. And we trace all these kind of APIs that we use in HPC. So we started with level 0 with the Intel CUDA, and then we added OpenCL. Bryce is big into the OpenCL community. And then CUDA runtime, CUDA driver. And then we added MPI with our communication network. And now we're starting added more and more libfabric and stuff like that. And maybe for you, what is important is like everything is in user space, right? We just LD preload something, we would generate tracepoint for application. And our goal was to be really, really easy for user, right? So for old people like me who remember the nice NVProf, you were just doing NVProf and then your binary, you got a summary. It was before they switched to Nsight, and now you need to have 10,000 commands to be able just to get a summary. So we are just that. So you put your name and you have a nice summary. And so at least people can know where is their bottleneck, right? If it is the communications, the GPU, stuff like that. And we rely a lot on FHOS tool, so LTTng and Babeltrace. So for example, here, it's a guy who runs for 10 minutes in our system. So for 10 minutes on one node, so one node is 12 processes. We have 6 GPUs, but we run 2 processes per GPUs. And so you should imagine that multiplied by 10,000. And you see the number of calls is start to be, I think I should start putting dot or comma or whatever, because now the number are so big it's hard to really count, but I think it's a few trillion calls. So this is the amount of data we need to profile. So depending where you come from, it's either super big or super small, I don't know. And so this is this kind of summary we want to see. So for example, here, we have different code MPI and stuff, and we want to generate this kind of summary at scale, at 10,000 node. So just people know what kind of, where they are waiting for. And when we did this project, we also realized that I say we are the team where we need to understand really what is going on because we need to find bugs. For example, people misuse the API. For example, they clean event before cleaning the event pool or stuff like that, or they forgot to synchronize. So what we want to do also with, I guess, the opposite of the summary is to see the full trace and to get all the information of the trace in a kind of a nice, pretty printable thing. So for example, we need to have the name of the enum. We don't want to have the enum values, and after we need to look at the doc to know what it is the values. So we have also a pretty printer of the trace. And also what it is important is like the trace gets the full semantic. So when we generate the trace, we dump absolutely all the values, all the parameter, because we need that when we have some bug and we need to understand what is going on. So we need to have all the information. So for example, some people in our group work on heap on top of level 0. So thanks to the ruling who say API are not copyrightable, now you have the lawyer green light to be able to do that. So it's just heap, a portable heap. And so we implement, and here you can see how, for example, heap is implemented on top of level 0, and you can see maybe if you have bugs and stuff like that. So it's very nice. For example, here we see the result is really the name of the enum and not the value with 0 or something like that. So it's really useful. And for the middle scale, what we have is also a visualization using protobuf and perfetto. I think so. We started that long ago when no documentation existed and everything, so it was a little challenging. I think now it has been really improved, the documentation. And we, as you saw, we generate trace greater than 2 gigs. So I'm really interested in case in the future days we'll see, at least my understanding, how we can load multiple traces. So it will be nice if we can bypass these kind of things. Because 2 gigs is not that much for us, so it will be nice if we can load bigger traces. So yeah, so TAPI is this 3 things. So a summary, a timeline, and a trace, and this is what we want to do. This is what at scale for at least the summary. So now it was a good story. I showed slide, it worked, and now the reality of all the problem we face. We are already a small team, so 2 permanent guys and multiple people who come and help, depending if they have time. We have 6 current providers of backend or frontend, depending how you see the thing we trace, the programming models that we trace. And I count, we have like 14K trace points, so independent event that we want to profile. And it is growing because we need to add more and more backend. And of course, the spec of CUDA, they evolve every month. So every month we need to maintain, we need to add new trace points, we need to do these kind of things. And for the analysis, so generate a trace is nice, but then we need to generate the summary, the timeline. We have 10 Babeltrace2 plugins. And we are only 2, 3. So it's a lot of work. So the goal was how can we handle such big number of trace points and this number of things, and to maintain that. I think maintenance is the most important point. As usual, everything can be solved with 1 layer of indirection, right? So we say, okay, automation, we'll just automate everything. It's too hard, and I think this is what the tool we developed to do that we want to discuss. So what we take is we take the official API, so we trace API, right? This is a good thing. It's like we know what we want to trace. It is what the vendor provide into their API header file, right? So they give us, for example, CUDA, have CUDA.h, and we want to profile all the call they put in CUDA.h, what it is visible to user. So we'll take the header and we'll generate everything automatically, all the LTTng Babeltrace point, and all the things we want to do the Babeltrace plugin. So everything will be totally automatized, and this is what I want to show you. So the first thing is H2 YAML, and This one is a tool will take the header, and from the header we generate a YAML representation, and from this YAML representation, it is kind of trivial, you can ask Olivier or some other people, to generate LTTng trace points. So it's just a script who will take the header provided by your vendor and generate a YAML representation. And then this YAML can be massaged to code gen a lot of trace points. And this is a kind of nice, so the good thing is you learn a lot of C and weird stuff. So this is the kind of stuff, for example, they do, depending on your level of C, this code is trivial or horrible. So for example, you have always forward declarations, then you have function pointer, then you have a function pointer, you know, who have like struct on these kind of things. You have anonymous enum and all of these kind of things, so you discover nice C stuff. You discover fancy, for example, I discovered, and in C, at least what Clang told me is a function, when you declare a function and you put just parentheses, empty parentheses, is not a function without arguments. This one is a variadic function, whatever. So if you look at the Clang AST, it will say function non-proto, you should put void. So you should do foo, parentheses, void, and this is a function without argument. I guess maybe it changed in different forwards in different system, I mean different version of the C spec. But at least you learn this kind of thing, so it was always nice to learn new C. So we take this kind of things that really, for example, CUDA, this one are more or less real examples that you can find in the CUDA.h. And then we generate a nice YAML who is more or less a translation of these kind of things. So for example, you know that like foo takes some parameters, the parameter is an enum or stuff like that, or it is a custom type who was const. You know, for example, that everybody knows that you're in C, so if you put this anonymous function, this one will have global scope, everybody will saw it, so we need to handle that, and we put it in the global variable who have no name, but you know that's the name of SO and stuff like that. So you have a lot of, yes?
The C++ is different. So
yeah, C++ is different, exactly.
Means no argument
exactly.
in C++, so that's the difference between C and C++.
Exactly, yeah, exactly. So you have all this kind of thing you don't want to know, but you need to know, you know, this is the thing you are forced to know. And so you generate this kind of YAML, and what we use to do that, and I think you have different parser for Clang. I guess you have maybe two. I think one is three-seater. This is what they use, for example, in VS Code to do some syntax lighting and everything. So the API, I think, is really nice to work with, but we were afraid that because they use it for syntax highlighting, they don't really care of parsing absolutely everything correctly, right? It's okay if they have a bug because it's just, you know, your VS Code will change the color of the syntax, it's kind of okay. But we were kind of paranoid because we already moved from an old Ruby parser and we wanted to be sure, so we used Clang. And I think Olivier showed us at the beginning, so it showed us proof of concept, so it was really nice. The problem is like this thing, so it's libclang, who is the front end of Clang, and you have a lot of idiosyncrasies that are really absurd, right? I think it makes sense maybe if you're a Clang developer, but it doesn't make absolutely no sense. No documentation, you know, the documentation is the doxygen generated from the source or something like that. And I will show you some of those here. So anonymous function, a pointer argument is impossible to get the name. Forward declare structs, they are parsed 3 times. Type def is super complicated and everything. So the funny thing is this one, if you use AI, you know, whatever your favorite model, you ask, oh, can I do that? It will just give you the doc, so you run the example, it is wrong. So it's really nice because they follow the documentation, they never already run the code. So they're absolutely sure this is how you should do it, and you agree with them because this is what the docs say, and you run, and it is not true. So it has been nice to see the limit of, for now they cannot really run code, so it's nice. And so we spend a lot of time, I spend a lot of time doing that, and now I think I'm pretty confident at least we can parse all the major header. We verify that it agrees with something. We have 100% unit test coverage, so everything worked well. So it's having pretty nice. And just to give you a little bit of the craziness is, for example, just to know if an enum or if a node is anonymous, they have a function which is called isAnonymous. But of course, you have 10,000 special cases that isAnonymous doesn't work. So you need to do all this crazy, the kind of code where you have more comments than actual line of code, and this is also the case. No need to go in the detail, it's really painful to do it correctly. And so it would be nice if some people, so if we agree in the same YAML, right, if we can be interoperable between tools, we have this format who describe maybe the AST or whatever, the intermediate format for tracepoint, something like that, so everybody can reuse, so already maintain, so we don't need to re-implement this kind of thing. Because, yeah, it's fun, but it's not really super specific and maintenance and stuff, so I don't want you to redo it because it's not really fun. For example, I spent Stack Overflow saved me, I think maybe the last time in my life, because now it's dead, but one guy 5 years ago said, oh, you should do that. And indeed, it was correct, so it was really nice. But yeah, maybe if you are interested for this project, it has been fun, and now we have everything packaged and everything, so it has been kind of useful to have this tracepoint. So this is the first thing, so now we know how, from the header file, we can generate a YAML representation, and from this YAML representation, I think it's pretty obvious. If you have all this information, it's pretty trivial to generate LTTng tracepoint or any kind of tracepoint because you have absolutely everything in a nice format that you can read. So you can just go with it, and this is how we generate our 10,000 tracepoint. So this is done, and now the maybe less discuss, at least this is what we saw, is now you need to analyze the trace, right? We have all this trace point and we need to do something with the trace. So LTTng is really, really efficient of generating the trace, and then we need to be able to analyze, to replay, to give something to our user, because okay, we have 1 terabyte of trace, is nice, but what we can do with it. And we need, so as we showed before, we need to generate a summary, all this big thing. We need to generate a timeline, we need to generate something. And what we do, we use Babeltrace2. So Babeltrace2 is really how you read CTF trace. And Babeltrace2, for the people unfamiliar, is a plugging architecture. So you chain plugging together. And so you need to write Babeltrace2 plugin, and then if people never use the API, so the API is really nice, really well described, lot of documentation, but it is kind of really verbose, right? It's low level C. So we have plugin, I will show you, is maybe 100,000 lines or something like that, because for each event, for each of these 12K events, we need a few lines to be able to decode the message, to unpack, and all of these kind of things. So they have Efficios have a Python API, but it is too slow for us. We cannot handle this one. So we need to write it in C, and it is kind of tedious. And also one of the problems is like we have users, we have custom who want to develop custom analysis. For example, they want to know their high watermark of memory usage for this particular part of their code and to verify that it matches whatever, all these kind of things. And Babeltrace2, if you want to write a Babeltrace plugin, it seems obvious, but you need to know Babeltrace2. So you need to know like all the CTF hierarchy, like the command context, what it is an environment, what it is a stream class, and all of this kind of thing. You need to be familiar for all of this concept where our users, they don't care. They just want to be able to analyze the trace. So what we do is, yeah, as I say here, it's like 15, I check one of our plugin, and as I say, we have thousands of plugin. It is maybe 100,000 lines of Babeltrace2. So we can ask user to write that, and us, we cannot ask ourselves neither to write these kind of things.
I just need to clarify. You said that you have 1,000 plugins, 150K log per plugin.
We have 10 plugins, yeah.
Okay, 10 plugins.
Yeah.
So you're at 1.5 million lines of code of plugins for Babeltrace.
Yeah.
Okay, I just want to make sure.
Yeah.
Okay.
So yeah, it's a lot because we have so many trace points. We need to aggregate everything and all of this kind of thing, each trace point and this kind of thing. So we started with, as project grow, you manually create lots of functions to help you to do the unpacking with horrible C++ template and stuff, and it was not really viable at long term when we start growing that much. So we are like, okay, no, we need to do something better. And we are like, oh, we are already generating automatically the trace point. Maybe we can generate automatically the Babeltrace. And this is what we did. So we take the YAML with more or less the old YAML we show you, and then we generate all the plugin infrastructure, all the unpacking. So now what they do is like the user, they just register a callback on an event they want to know. And that's it. And now they have a callback and they can do whatever they want. So now the user doesn't need to know anything about Babeltrace2. The only thing they need to know is like their event and what they want to do with it. So for example, every time they have a memory, they can just increase their counter, and they freeze, they just decrease the counter. And now it's super easy for even new interns who come to the project to write new plugin or to maintain new plugin or to refactor plugin because they don't need to know about Babeltrace. And the opposite for us is really nice because we can just focus on Babeltrace, removing all the error code, do all the nice checking and stuff like that. So they've been really useful. So same kind of YAML. So for the people familiar with Babeltrace, here you already see, so it's really, because the doc are so nice, it's super easy. We take the doc and we just write kind of a YAML with a one-to-one mapping. So you have a string class, you have an event context field class, and then you have all these kind of things, and then an event class and all of these kind of things. So this one are already, if you are familiar to Babeltrace2, it should be really obvious. And it is really we did the one-to-one translation of the API, of the hierarchy of the API into YAML. So it's pretty, so you can think of that as a serialization of the metadata of the trace. And then from that, the only thing a user needs to do is to write this kind of code. So for example, we can start from the bottom. So the plugin, a MetaBabel plugin, is just they need to expose one function which can register user callback. And then we'll call this function, and this function will register a lot of callbacks inside your API. So for example, here, what the user says is like, okay, I want for this event that we know exists on the trace, we call getPlatform IDs. Every time in the trace we will read the getPlatform IDs, we'll call this callback. And our tool, MetaBabel, will do all the unpacking, all the handling of everything. So we'll give you a callback where it is all the data we have been unpacked. So for example, the name of the event, the VTID, the num tree, and everything. So it's really nice because here you have nothing related to Babeltrace. You just have, okay, I just want to have a callback because I receive this thing, I receive an event, I want to trigger my user code with a lot of things. So it is written in Ruby, and so it's called MetaBabel, and here you see, okay, I just want to create a sink, so you have sink filter and everything, so it depends where you are on your node of your graph, and you just pass what you get upstream, so what kind of message you want to update, to unpack, and for example, you pass the YAML. So in our case, we pass, for example, the YAML we generate for the CUDA API. And then MetaBabel will generate this 100,000 line of C to do all this kind of unpacking and stuff like that. And then you just need to compile everything. It's just one line. You include all the things generated by MetaBabel and your code that you saw here. And now you have a valid Babeltrace2 plugin, and the only thing you need to do is now when you create your graph in Babeltrace2, you can just pass those plugins. And so what we use is a CTF reader, for example, and after a lot of filter and all of this kind of thing, to be able to create this summary. For example, we do a tree aggregation of summary, who is able to scale to 10,000 nodes, right? You cannot do an aggregation of 10,000 files. So what we do is per node, we do the aggregation, and then at the end, we do the aggregation of the aggregation. So we try to do local analysis of everything. But the good thing is just Babeltrace2 plugin, so it's really nice, and everything is automatic. The only thing we need to do is to change the callback if people want to use, but we have a way of matching callbacks and all of this kind of thing if you want to be far more portable and stuff like that. So maybe this is the trick is this is how we handle all our plugin. Now all our plugin is handled with MetaBabel. It saves us a lot. I think when I did the PR, I was really happy because I think I removed like, I don't know, 20,000 lines of code for my repo when we switched to handcrafted Babeltrace2 plugin to MetaBabel. It had been a really good PR. Maybe it worked for us because we know statically all the events we have, right? I think this is a key point. It's like we know, because we are generating our trace point, so we know statically everything we got, right? We know the full set. It's not like if you are general, for example, a general pretty printer will not be able to know which kind of message they have and everything. For us, we know absolutely everything. So we can do also static analysis. For example, if you register a callback who doesn't exist, we give you an error and all of this kind of thing. Or if the type is incorrect, we give you an error and stuff like that. So we have a lot of type safety because we are static. So if it is your case, I think it's really nice. I think we maybe doesn't discuss that much the analysis of trace. So it's really nice. Please try or give us feedback. One limitation we have right now and we want to work in the future is the performance of Babeltrace2. It's a little slower, far slower than LTTng. So it's far faster to generate trace and to analyze trace. It can be, for us, it's a bottleneck. So for example, right now we have user waiting for 6 hours, right? For example. So it starts to be long. So at least it's still better because it's running, it just takes time. But we want to improve performance. The good thing is now that we abstract everything away. In theory, we can even remove Babeltrace2 if we really want. We can write our own CTF reader, but I think what would be more possible is just to work with FissueOS to how to improve, give us maybe some unsafe API without any type checking and stuff like that. So it is a possibilities. So to finish, we are a small team. We have a lot of trace points. I mean, a lot. I don't like to use a lot because it really depends. I'm pretty sure some people working at Google, for them it is nothing. They have 10,000 more. But for us, it's a lot. So we need a lot of automation because, yeah, it's really not the most fun part of maintaining your code when they add a new version of CUDA with v6 on the name and you need to regenerate everything and stuff like that. So we did a lot of work on that, and it's got two parts. One, it is this generator, this libclang tools. We take your header, CUDA header, and just generate a YAML. So then you can use this YAML to do a lot of kind of tooling, for example, pretty printing and a lot of this kind of thing. And then we have the MetaBabel, who can use like Babeltrace2, who generate Babeltrace2 plugin. So you don't need to write Babeltrace2. Python binding at a little high level is really more useful, but it's really slow because now you have the Python overhead and all of these kind of things. So I think MetaBabel has been a really nice middle ground for us between performance and usability. And that's it. I think it is my end of slide, so I don't know. If you have any questions, thank you very much, and yeah. Yeah, clap, don't clap.
Okay, I'm actually very excited. I love tools that make us do less work. And so, MetaBabel, has it been able, I imagine that by reducing the amount of code you have to generate, it reduced the amount of bugs you generated too.
Or it multiplied by the number of plugins you. So if you have a bug, but no, yeah, far less bug, yeah.
Okay. The other question, so let's say things, like you got it perfectly. I'm not going to get perfectly on the first shot. What kind of debugging flow would we have with MetaBabel?
Yeah, so I think one of the big advantage is because we can statically type. So for example, as a user, one of the bugs you do most of the time is here when you register the callback. You don't put the correct function signature. And now we can statically verify everything. We can say, okay, no, you try to unpack to get platform ID, but the function signature didn't match, so we'll give you a nice compilation message telling you, yeah, it doesn't match, so be careful. You try to use this function pointer, but it's not the function signature. So all of these kind of things for us is really the most important. And then we just generate nice Babeltrace2. So if you have a bug during Babeltrace2, but as you said, we generate so many plugins now, we have a lot of tests. We never saw any bugs in Babeltrace2, so most of the bugs we found are user bugs during the creation of the plugin. So it's, I think, pretty robust. I don't think we didn't see anything. Yeah.
Okay, cool, thank you.
Yeah. Yes?
And you're saying, is MetaBabel just available on the internet, like if we look it up?
Oh yeah, good point. I didn't put the link. Yeah, good point. Yeah, it's called MetaBabel. I think if you Google MetaBabel, you should be able to find it. Or my name, Aplancourt MetaBabel, I think. And it's just a Ruby script, so nothing to install. I mean, Ruby, sorry. I guess everybody, yeah. At least it's no scheme, huh? So, or Haskell or something like that, but yeah. So you just take it and you have it.
And then also in terms of, like one of the things you had talked about is being interested in sort of having an agreement on what the intermediate trace point format would look like. Do you have, is the code that you use to generate the intermediate formats also available somewhere, or is that something that you?
Oh yeah. So we have, so we have two tools. So one is, we have two formats at least. So one is, I think this one with the format for MetaBabel. I think this one we should agree pretty easily because it's really a one-to-one mapping from the documentation. So I think this one is not at all contentious. I think this one can be pretty easily agreed because we just take the thing and it is really a one-to-one mapping from the doc. So, and this one, so this one is easy. The hardest one is maybe the one with for the LTTng trace points. This one is far more contentious because I think this one you have a lot of, how to generate this kind of thing. Here we found this kind of agreement. So, and the translation between this guy and the other guy now is not yet public. It is ready because you need a lot of meta information. For example, you know if you have a pointer, you need to know if it is an in pointer or an out pointer. You need a lot of metadata. So this one is not yet. It's ugly, horrible, hacky script everywhere to be able to do the translation between the two. So I think that one.
To get to this point though. Like
Yeah, so this one, yeah, exactly. So this one is H2 YAML, so you just use H2 YAML. So and it would just generate this thing out of the box, and this is the only thing they are doing. And then to go from this one to this guy, it's more. You need a lot of massage to be able to know all these kind of things.
Thank you.
Yeah, no problem. Yes?
From a YAML file, generally from a C header files, like how do you select some functions, some instruction to trace, or you just put trace points for everything?
Yeah, this is a trick. Yeah, we are not smart. We trace everything. So I think CUDA have maybe 8,000 CUDA in CUDA header between the runtime and the driver. So we just regenerate 8,000 trace points, and we trace absolutely everything.
It's automated, right?
Yeah, it's automated. This is why for us it doesn't change anything. And I think it's too complicated. So what we do is we let users, if they want. So one of the problems is people spin locking on some API. For example, they spin lock over CUDA synchronize. Spin locking generates 1,000 million events in 2 seconds, right? Because this guy just spin lock, and so your trace is just full of this thing. So we allow user to say, okay, -- no, don't trace this API call because I know I will spin lock and stuff like that. Maybe in the future, what we want to do is some spin lock detection, I suppose. If the user starts generating like 1,000 calls per second, we just disable it for a few times or stuff like that. But right now, we are stupid. We just generate absolutely everything and trace absolutely everything. Yes?
Curious, actually, about the spin lock issue. I was actually wondering, because we did this with function tracing, for a lot of functions, we actually have this in the kernel. I don't know if this might be something useful in the kernel, is having, when there's duplicate events, to just say, have it be able to detect, oh, this is the same as the last event, or maybe if you see 2 or 3 the same, have like a throttle, say, okay, stop recording.
Yeah, exactly.
And then as soon as you have another one, just record the last event, and then like basically have a buffer there, just keep basically dropping events until you see an event, and then boom. Then it probably gets rid of the issue of like 10 billion,
So that's something we plan to build on trace counters. So we have planned for 216 aggregation maps in LTTng. So there we can keep counters of events, and then we can build on top of that detection of multiple duplicates and things like that.
So actually, it's something I've been thinking about adding to actually the ftrace Spring Buffer 2 is to have, because we do it for function tracing. There is actually a buffer for function tracing when there's a lot of functions being duplicated. There's an option to say, ignore duplicate functions. And then, but that save it still does the work, but it doesn't waste the buffer.
Exactly. Yeah. And also one of the issues that those calls, because the spin logs are super low, so when you, but the overhead of the trace points start to be really high compared to the, so when you do the total, the summary, you think you spend 2 minutes or 2 hours, but in fact, no, it's just the overhead of calling this thing and everything, right? So even the timer you got from spin locking are totally wrong and misleading, so it would be far better to just avoid or to put a little star to say, okay, this number take with caution or that doesn't reflect, because yes, this one was, it beat us a lot, the people spin locking.
You have the same issue with people who like run function graph tracer and they'll see like these higher level functions saying, my God, it took so long to run, but they can know the function graph tracer adds an overhead.
Exactly.
Like those functions at the top level are now, they're tracing thousands of events and every one of those events adds up.
Exactly. Yeah, we have exactly the same issue.